Aloha and welcome to week 4, all about sediments. This is lecture 1 of week 4, where we're going to talk about the types of sediments and where they come from, and then a little bit about how sediments are classified. So, why do we care about marine sediments? So, they can help us record everything that's happening on Earth, essentially. They can help us look at climate change, sea level change, ocean chemistry, volcanic eruptions, past ecosystems, human impacts. Again, sediments tell part of Earth's story. So, since they help us understand so much, we need to understand what they are and where they come from. This is 4 different cores of sediment from the southeast coast of Britain. And they look really different, right? They show different time periods. One has a lot more clay in it, one is a lot more sandy, and this is showing the difference in time. And we'll talk about why that might be a little bit later. There are 4 main sediment types. We classify them based on where they come from. So lithogenous or terragenous come from land. So they come from the land and then fall into the ocean at some point. Biogenous come from biological organisms. Hydrogenous come from the seawater. They're, like we talked about with the hydrothermal vents, the minerals are precipitated out from the seawater. So that's where hydrogenous sediments come from. And then cosmogenous come from space. They're the least common, but they come from space. So first, we're going to talk about lithogenous sediments. These are the most common. They come from the weathering of continents. So essentially, when the wind blows and it blows sand or rock into the ocean, that's where these lithogenous sediments come from. They can also be transported by rivers. Think about a river delta, glaciers, landslides. There are a few different ways, not just the wind. They, again, are the most common of all the sediments, and they are dominant on continental margins. For context here, we don't have a whole lot of rivers. We have a couple, but mostly, if you think about what our beaches are made of, they're made of biogenous and volcanic sources. And, there's some lithogenous, but a lot of it is the black sand coming from volcanoes. And a lot of it is also crushed up coral. That's a lot of what makes sand as well. Here is a river delta. You can really see the sediment coming out from that river into the ocean. So this is a huge source of sediment near this river in Africa, the Zambezi River in Africa. Biogenous sediments are made from the skeletons and shells of mostly ocean organisms. Calcareous ones made of calcium are foraminiferans, coccolithophores. Siliceous is kind of a funny word, but it means they're made of silica, like glass essentially. Diatoms and radiolarians. And we'll look at all of them. They're actually really beautiful, especially diatoms and to some extent radiolarians. They're really interesting to look at and cool to see. So those biogenous sediments can tell us about temperature in an area. They can tell us about productivity, nutrient availability, and sometimes even water depth. Here is an image, a microscopic image of diatoms. This is hugely blown up. They are microscopic, but really interesting shapes and really delicate and different. And then here we have radiolarians, also really interesting shapes, a lot of variety here. Again, these are hugely blown up for you to see, but they're really, really interesting little organisms. Part of what make up the plankton that we'll talk about way later in the semester. Hydrogenous sediments form by precipitation, so they come out of the water. Manganese nodules are probably the most famous one. Metal sulfides, when we talked about hydrothermal vents, we talked about some of the metal sulfides that form at the hydrothermal vents, evapoporites, and ooids. These all show us a lot about the ocean chemistry and the circulation around that area in the deep sea. Here is a picture of manganese nodules, and you can see that a manganese nodule is essentially starts off as some form of sediment, like a rock or something that's more likely to be lithogenous, and then the manganese forms around it over time, which I think is kind of interesting. Cosmogenous sediments, very rare, but distributed fairly evenly across the globe. We have micrometeorites and microtectites, and they essentially help us date sediment layers and identify impacts that may have happened over time. The microtectites are essentially almost like glass. Here, we'll look at these are microtectites. Um, and they form, when the impact happens, they form these glassy sediments. And I would love to find one of these. I think they're beautiful. I would love to find one in real life. If anybody's ever found one, put it in the discussion for me. I'd like to know about it. Okay, then how do we classify sediments? For the most part, we classify sediments by size. We already classified them a little bit by origin, right? But then we go size, smallest to largest to smallest. So we start with something like a boulder, a big old rock, a cobble, a pebble, gravel is sometimes included in here. Then sand, silt, and clay. Clay is going to be our tiniest grain size. Um, Grain size shows the energy in an environment. So if we think about a beach that has huge waves crashing in all the time, there's a lot of high energy there, we are not going to see the tiniest forms of sediment. We're not going to see much clay or much silt. We'll see things like boulders and cobbles because they can withstand that high energy. Whereas if we have a really, really calm bay without much wave action, clay and silt will build up. And if you've ever walked into the water at a very, very calm beach, it's usually a lot more mucky, for lack of a better word. It's usually a lot more fine than it is in a higher energy area. So here's an example that I like to think about. If you have ever been on the Kona side of Hawaii, the big island, and you've gone to the beach at the pier, there are two sides there. There's the pier, and on the Ali'i side is what we call the swimming beach. And the sand over there is typical sand. Like, it's pretty normal. It's not got huge rocks in it or anything, but it's pretty normal Hawaii sand. If you go over to the other side where the hotel is, where the King Kamehameha Hotel is, and you get in the water there, that sand tends to be more silty. It's not really clay, but there is silt there. If you walk around on it, it feels almost like flour. Silt is kind of the consistency or the texture of flour, like baking flour. And when you walk around on that, you can feel the silt under your feet. And people always ask why it's different on the two sides since they're right next to each other. And it's because on the hotel side, there isn't as much wave energy. It's really protected because of that very narrow canal where the boats come in. And other than that, there isn't a whole lot of wave action coming in there. So it makes a huge difference. Okay, let's move on. And here you can see sand size. You can see very coarse sand, fine sand, very fine, and medium sands. And you can kind of tell the difference there. I think that's fairly self-explanatory. Sorting is another way that we kind of classify and tell the difference between different beaches, different amounts of sediment. Well sorted means that it's consistent particle size. Means that for the most part, the particles within a sample, like if I were to take a handful of sand from, the swimming beach, if I took a handful of that sand, it's mostly going to be the same particle size. That means it's well sorted, and that means that the energy is fairly consistent in the area, at least at that particular time. Poorly sorted means that we have a very variable particle size. And we'll look at some examples here, but I might pick up a scoop of the sand and have some rocks that are bigger than my finger, and I might have some teeny tiny particles and everything in between. That would be a poorly sorted sample. And that generally means that the energy on that beach changes quickly, and it doesn't stay the same. So if you look at this sand, would you guess that it's well sorted or poorly sorted? Do the grain particles look the same throughout the sample, or are they different? In this one, they're definitely well sorted. They're all pretty much the same on this dune. And that means that the wind that blows on that dune is fairly consistent. Now, over here, we have a different beach, a very different looking beach. In this case, would you say that the particles are well sorted or poorly sorted? I see some huge boulders. I see some fairly coarse sand down here. I see some pebbles. I see a lot of difference here, which leads me to believe that this sediment is very poorly sorted, which would lead me also to believe that it has a very variable energy here. Like it looks like that water is very calm right now, but I would guess that in another day or two or something, we might get huge waves coming in that remove some of that sediment and that make it very variable. Here's another two options to think about: well sorted or poorly sorted. I would say it is more well sorted than this one, but less well sorted than this one. So it's definitely a range here, a continuation. Okay. So I would still say this is pretty poorly sorted, but not the least poorly sorted. And you can also see a a biological component here. We've got a crab molt. We'll talk about crabs and how they molt their exoskeletons later in the semester. But we've got crab molt. We've got, that looks like some kind of plant material here. This honestly looks a bit like a bone to me. Looks like a vertebrae of something. So this is a pretty interesting beach. There's a lot going on here. And then what about this one? Clearly volcanic, right? We've got a beautiful black sand beach here, and that grain size looks pretty consistent. So I would call that well sorted again. Okay, so this lecture, we talked about the sediment types, where they come from, grain size, and sorting. And everything this time came from chapter 12 in your textbook. And up next, we are going to talk about how sediment moves around, and the energy involved in that a little bit more. We started to talk about energy, and we're going to get more into it in the next lecture.